All right, let's jump right into this explainer. Today, we're going to reverse engineer the mechanical architecture of what is undeniably the most famous firearm in human history. We're looking at the raw engineering behind the AK-47's indestructibility. Now, you hear a lot of myths and legends about this machine, but we're going to completely bypass the folklore today. Instead, we're going to look strictly at the blueprints, the physics, and the incredibly brilliant, calculated design choices that actually make it tick.
Just to wrap our heads around the scale of what we're talking about, look at this number. Over 100 million AK-47s have been produced since 1947. I mean, that's just staggering. And this weapon has a legendary reputation for a reason. It's been buried in sand, completely submerged in swamps, abandoned in dense jungles for literal decades, and incredibly, it still fires. But as engineers and analytical thinkers, we really have to ask ourselves how.
That brings us to our core question. What makes it functionally impossible to stop? Well, I want to reframe how we think about this weapon right from the start. This reliability, it isn't magic. It's not some lucky accident of history. It is entirely deliberate, carefully calculated engineering designed to solve a very specific set of problems. Mikhail Kalashnikov built an architecture that practically defies failure.
So, here's our blueprint for this explainer. We're going to start with the tactical problem it was meant to solve. Then, dive into the long-stroke gas system, the completely counterintuitive use of loose tolerances, how it was stamped for mass production, and finally, the ultimate engineering trade-off. Okay, starting right off with Section 1, the tactical problem and designing for the absolute brutal reality of the Eastern Front. To truly get the engineering, you have to understand the tactical reality of 1944. The Soviet Union was deep into the most brutal land war in modern history. The standard Soviet infantry rifle at the time was the Mosin-Nagant. Now, it was accurate, it was powerful for sure, but it relied on a manually operated bolt. The shooter had to cycle every single round individually. But by 1944, German forces were deploying the STG-44, which was the world's first mass-produced assault rifle capable of fully automatic fire. Soviet infantry were facing a massive firepower gap at close and medium ranges. They desperately needed an answer that could deliver automatic fire, but here's the catch. It also had to be operable by a conscript soldier with bare minimum training.
And on top of that, they needed it to work here, minus 40 degrees Celsius. The Eastern Front presented just an extreme environmental baseline. We were talking about sub-zero temperatures, thick mud, abrasive dust, basically conditions that would systematically destroy precision mechanical equipment within hours of being deployed. So the engineering requirement was incredibly strict. Build a weapon that survives this. Kalashnikov's answer wasn't brilliantly complex. Actually, it was brilliantly simple.
That brings us to our first mechanical pillar, Section 2, the long-stroke gas system and how it keeps the mechanism clean.
The AK-47 operates on what's called a long-stroke gas piston system. Let's walk through the mechanics together. When a round fires, step 1, propellant gas is bled from the barrel through a port located about 250 millimeters from the chamber. In step 2, that gas shoots up into a cylinder located just above the barrel. Now, step 3 is the crucial one. The gas drives a piston rearward. In a long-stroke system, this piston is actually permanently attached to the bolt carrier, so the entire piston and bolt carrier assembly travels backward as one single heavy unit. It compresses the recoil spring, extracts and ejects the spent casing in step 4, and then finally in step 5, the spring pushes the whole shebang back forward to strip and chamber the next round. Now compare this long-stroke system to the direct impingement system used in the American M16. In the M16, propellant gas travels directly back through a tube and actually vents inside the receiver itself. But the AK-47 system keeps that high-temperature, carbon-heavy propellant gas entirely outside the receiver. The bolt failure group stays so much cleaner for so much longer, and since carbon fouling is literally the primary cause of mechanical failure in automatic weapons under sustained fire, by keeping that fouling far away from the critical moving parts, Kalashnikov created a massive fundamental reliability advantage in the field.
Let's move to our second mechanical pillar. Section 3, deliberately loose tolerances. This is a genuinely fascinating, completely counterintuitive piece of engineering.
I absolutely love this quote from our source materials. By the precision standards of Swiss watchmaking or American aerospace manufacturing, the AK-47 is a rough instrument. To a traditional engineer, the mechanical decisions in the AK-47 look like literal fatal flaws on paper. The gap between the bolt carrier and the receiver walls is measurably larger than in comparable Western rifle designs. The components fit together with a highly perceptible, super obvious play to them. But here's the big secret. That roughness? It is completely intentional.
Just consider the physics of how debris interacts with these machines. Under tight tolerances, when you introduce sand into a precisely fitted weapon, those abrasive particles lodge right between the closely fitted components. They create immense friction, the bolt carrier stalls out, and the shooter is left holding a non-functional chunk of metal. But with the deliberately loose tolerances of the AK-47, those exact same sand particles enter the exact same gaps and just pass straight through. There literally isn't enough contact between the metal components for the particles to generate meaningful resistance. The weapon just keeps on cycling. Plus, remember that -40-degree environment? Metal naturally contracts in extreme cold. Tight tolerances seize up entirely when that happens, but the AK-47's loose tolerances just absorb that severe metal contraction and keep right on working.
All right, let's move to Section 4, Stamped for the Masses. This is our third mechanical pillar, and it focuses heavily on manufacturing and logistics.
In the standard production AK, the receiver is manufactured using a process called stamping. Stamping, or cold forming, is basically where sheet metal is pressed into shape under massive force, rather than being carefully carved or machined out of a solid block of steel.
By utilizing stamped sheet steel, the Soviets unlocked drastically faster production times, and it required significantly less raw material. But the real genius is right there in the third point. It uses standard industrial press tooling. This completely eliminated the need for specialized gunsmithing equipment. A standard run-of-the-mill factory with industrial presses could pivot to manufacturing these receivers in massive volumes. So this wasn't just an engineering choice. It was a pure logistics strategy that allowed production, distribution, and replacement at the unprecedented scale of a mass infantry army.
However, do not confuse rough manufacturing with weak engineering. Despite the stamped receiver and those famously loose tolerances, the really critical elements were vastly over-engineered. For instance, the AK-47 features a rotating bolt that locks into the barrel extension using two exceptionally large locking lugs. The surface area here is massive relative to the bolt diameter. This effectively distributes the intense chamber pressure of each firing cycle across a very wide contact area, drastically reducing stress concentration and extending the lifespan of the mechanism through decades of sustained automatic fire.
Which brings us nicely to our final section, Section 5, the ultimate engineering trade-off. Let's see how all this builds into a much bigger picture of design philosophy by comparing the AK-47 with its primary Cold War counterpart, the M16. The contrast here is incredibly revealing. In absolute terms, neither weapon is better designed than the other. They both simply reflected their design specifications perfectly. The M16 was engineered for accuracy and low weight. It was ideal for a professional army with robust logistics, relying on clean operations and a direct impingement gas system. But, as we know, in the early years of Vietnam, under sustained fire in harsh conditions, that system fouled rapidly, leading to tragic mechanical failures. The AK-47, conversely, was built for a mass conscript force operating at the very edge of its supply chain. Its absolute priority was pure reliability and manufacturability, utilizing the long-stroke piston to conquer mud, sand, and extreme cold.
So, as you can see, every single feature we've discussed today was a calculated trade. Kalashnikov knowingly accepted a modest reduction in accuracy at long range because precision was deliberately sacrificed for durability. Complexity was sacrificed so standard factories could actually manufacture the thing. Refinement was sacrificed to ensure extreme reliability in the absolute worst possible environmental conditions. The simplicity was always a deliberate engineering choice, not a limitation.
And that leaves us with this incredibly impactful thought from the source text. The AK-47 did not survive 8 decades because it was the most advanced weapon available. It survived because it was engineered to work when nothing else would. I mean, that is a completely different kind of engineering excellence. It's an architecture built entirely around extreme, undeniable function.
So I'll leave you with this final question to ponder. How might prioritizing durability over precision totally change the way we engineer the critical technologies of today? If we applied this brutal, function-first philosophy to modern systems, how much more resilient could our world actually be? Thank you so much for joining me for this explainer, and keep asking those big questions.